Hello, in this video we will look at the ways to calculate the mean or expected value, as well as the standard deviation for a discrete probability distribution based on a discrete random variable. Recall that the mean of a discrete probability distribution is also known as the expected value. So any questions that you see that ask you to find the expected value, we are looking for the mean. There's a formula on the screen. The mean of a discrete random variable x can be found by finding the sum of the x value times the probability of x value, or x times p of x. So again, this is the population mean, symbol mu, and this represents the sum. There's another video that describes this in more detail and shows the process by hand. We're not going to worry about that today. In this video, we're going to focus on how to calculate the mean and standard deviation for this discrete random variable using Geogebra. So example 4.5 says, find the expected value of the number of times a newborn baby's crying wakes its mother after midnight. Let the discrete variable represent the probability that a newborn baby's crying wakes its mother after midnight in a given week. All right, so our variable x is number of times a baby wakes its mom in 1 week. So what we want to find here is the mean and the standard deviation. If you look at the very top of the screen, it says the mean is also known as the expected value. So the question is asking us to find the expected value, which is the expected number of times per week a newborn baby's crying wakes its mother after midnight. So for this, we're going to use Geogebra. We're going to define two different variables. We're not allowed to use the letter x in Geogebra. So in this case, we're going to use the letter v for variable, or whatever other letter we want to. And then we're going to use the letter p for the probabilities. Just because I am going to try to split screen these, I'm going to do the typing here, and then I'll copy them into Geogebra. So I'm going to write v equals, and then I'm going to use the curly bracket, 0, 1, 2, 3, 4, 5, 6, 7. Close the curly brackets. So that will be our variable. And then we'll also write p equals, curly brackets, 2 divided by 50, 10 divided by 50, 21 divided by 50, 9 divided by 50, 3 divided by 50, whoops, I messed that up. 3 divided by 50, 2 divided by 50, 2 divided by 50, 1 divided by 50. All right, so I have my variables defined. I have my lists defined, as these are fractions or division steps. We can just write these in with the slashes. Now I'm going to go to Geogebra, and I'm going to drop those in there. I'll do a future example where I'll actually type it in, and I'll show how to use the on-screen keyboard. So V is the list here. P is the list here. And now all I need to do is find the mean of P. I made a mistake. That is not what I meant to do. I meant to find the mean of the variable along with the probability. I had the wrong thought in mind. To find the mean of the variable along with the probability, the mean of v comma p is what we actually want to type in. My apologies. So therefore the mean, or the expected value, would be 2.4. So we would expect this newborn baby to wake its mother 2.4 times per week. Again, the mean and the expected value. Now to find the standard deviation, we will type in the correct way this time is STDEV. Now there are two different options for the standard deviation. This is for sample, this is for population. Because we're dealing with a probability distribution, we're always going to use the population variables. So we're going to find the standard deviation of the population using the STDEVP function in GeoGebra, and we'll get us 1.456 or 1.5. All right, a couple things about the probability distribution. First is that we are always working with population variables or population calculations. This is super important because we are talking about a theoretical future value that cannot happen. There is no way that a baby will wake its mother 2.4 times in a week. A baby can wake its mother 2 times in a week, or a baby can wake its mother 3 times in a week, but there is no way of waking it 2.4 times in a week. So basically this number represents that if we were to look at many, many, many babies and many, many, many mothers and many, 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 many weeks, we would count the number of times that those newborn babies woke their mothers during many of those weeks, and we would add them all up, divide by the number of experiments we've run or the number of weeks that we have observed, and we would find that the average would approach 2.4 times in a week. The other thing about a discrete probability or a discrete random variable is that the sum of the probabilities must all equal to 1. So the sum of all the p's must equal 1. Let's just do that quick calculation. 2 plus 10 is 12. Since we have a common denominator, I'm just adding the numerators. Plus 21 is 33. Plus 9 is 42. Plus 3 is 45. Plus 2, 4, 5 is 50 with a common denominator of 50. So the sum of all these probabilities is 1. All right, we have another example for this video. It says example 4.6, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. What is the expected value? So again, the variable is number of times the call bell is pressed. We want to know how many times should we expect the call bell to be pressed during a 12-hour shift. We have our variable and our probabilities here. Okay, so I have split screen my computer so I can show how to use all the calculator entries here. Let me delete the prior entries so we have a nice clean screen. All right, so again, I like to use the letter V for the variable. In this case, I'm going to type in V, go to 123 equals. Now it's a little bit confusing because all the different brackets are in different options here. We're going to use the 1, 2, 3, the f of x, and the ABC key for all of these. We'll type in 0, 1, 2, 3, 4, 5, enter. And then I like to use the letter P for the probabilities. We need to go to 1, 2, 3 equals, curly brackets are in f of x, and then go back. Again, since these are fractions, we're going to type them in as a division, 4 divided by 50. Now, the only thing that's a little bit confusing is as soon as we make this, I forgot about this part, as soon as we make this a fraction, we need to use the right arrow to get out of the denominator. So we're going to need to use that right arrow every time. 8 divided by 50, right arrow, comma. 16 divided by 50, right arrow, comma. 14 divided by 50. I did not show that in the first example, so hopefully you guys are watching this video long enough to see what I'm doing now. Use the right arrow, comma, and then lastly 2 divided by 50. And we just press enter. Now, I was saying before that all of these values, all of the probabilities must add up to 1. We can do that really quickly by doing the sum of p and confirming, the sum of p, all of the probabilities add up to 1. So that works. We don't need that for this calculation. I was just showing you. All right, from here, we're going to calculate the mean. It's asking us to find the number, or the expected number of times that the call bell is pressed. So the mean of one variable, v, but we need to take into account the probabilities of those variables. So the mean of v comma p is what we're looking for, and that is our solution. So the expected number of times the call bell will be pressed is 2.32 times. Again, we showed with GeoGebra that the sum of p of x is equal to 1. We have one more example prepared for today. Suppose you play a game with a biased coin. A biased coin just means that the coin is an unfair coin, meaning that it's going to land on one side more frequently than the other side. You play each game by tossing a coin once. The probability of heads is 2/3. Oh, that's where that biasedness is coming in. It has a higher likelihood of landing on heads than tails. If you toss a head, you pay $6. Ooh, paying $6. I don't like to pay $6. That means that we are losing. If you toss a tail, you win $10. If you play this game many, many times, will you come out ahead? All right, well, the first thing we need to do is define the random variable x. So the random variable is a discrete random variable. It needs to be a number. It needs to be a counted value. The only way to do that is to look at the experiment. The experiment is to toss a coin once. Well, if I toss a coin once, I have two outcomes, either heads or tails. So we need to come up with some way of making a number value for a head or a tail, which we have with our money values. So in this case, the random variable x will be the money values of each toss, or each outcome rather. So the money value for winning is $10. The money value for losing is $6, but since we're losing it, we're going to put it as a -6. The probability of winning, well, it says here that the probability of landing heads is 2/3. The probability of tossing a head, the outcome for tossing a head is to lose $6. Using the fact that the sum of the probabilities all add up to 1, we can then find the complement of losing, or subtracting from 1, we'll get 1/3. Now we can just jump to GeoGebra. Let me show my discrete probability distribution, which is step 2. Complete the following probability distribution. We've done that. Let me delete all of this stuff. Delete. Start with a nice clean screen. All right, so again, I like to define my variable as v. V equals curly brackets, either $10 or -$6, and my probability p equals curly brackets again. What do we got? 1/3 for winning, 1 divided by 3. Use the right arrow, comma, 2/3 for losing. Enter. And from here, we can type in MEAN, open parentheses, V, comma, P, enter. And we get that our mean, mu, is -67 cents. So if we were to play this game for a really long time, we would expect to lose money after many plays. All right, so two things about this. First, there is no way of tossing a coin once and losing 67 cents. If I toss a coin once, I could either win $10 or lose $6. If I toss a coin twice, I could either win $20. If I get tails, tails. I could lose $12 if I get heads, heads. Or I can win $4 if I get a head and a tail in either order. So there's no way of getting 67 cents. However, if I play this game repeatedly, the average of all of my winnings will come out to 67 cents in the negative. Second thing I want to say is that if we were to look at this distribution. It's a pretty straightforward distribution. There's only two different outcomes. I'd probably skip the calculator for this one and just do this by hand. We can find or define a third column. This third column will be the x value times the p of x. So 10 times 1/3 would just be 10/3, and -6 times 2/3 would just be -12/3. And if we were to add up x times p of x, let's shift that over just a little bit. If we were to add up x times p of x, this third column, we would get -2/3, which is where we got the mean from. All right, I hope this video helps.